We're very glad to have this week as our speaker, Danny Nam from Princeton, who's a student of Allan Sly, who's going to talk to us about critical 1D multi-particle DLA, joint work with Dor Elboim and Allan Sly.
Oh yeah, thanks for the introduction, and it's a pleasure to be here and speak here. So today I'm going to talk about a recent joint work with Dor Elboim and Allan Sly. Dor is a fellow grad student at Princeton. Allan is my advisor. So some of you may have heard about the diffusion limited aggregation model, which is a model of fractal growth. So initially, there's a single frozen particle at the origin of your domain, and then the particles enter one by one from infinity by performing a simple random walk until it touches the existing aggregate and freeze together, and then the next particle enters and it repeats. So the top right picture is a simulation, and the bottom right is what we can actually observe in the nature. So mathematically, this is believed to be a very difficult problem in the sense that even the very basic questions one can ask are left open. So for instance, if xn is the diameter of the fractal after n particles have entered, then we kind of don't have a rigorous result on how xn should scale, for instance. So today's talk will be on a variant of this model, which is a multi-particle DLA. So previously, the particles entered one by one, but now we will have a sea of particles spread all over the domain according to some prescribed density lambda. And every particle performs an independent continuous time simple random walk until it attaches to the existing aggregate and freeze together. So a naive intuition one can think of this model is that if the overall density of the particle is low, then there will be fewer particles and then the aggregate will grow slowly. On the other hand, if the density is higher, then the aggregate will grow faster. Interestingly, this growth rate differs in terms of has two different behaviors in dimension d equals 1 versus dimension d equals 2 or higher. So when d is 2 or higher, it's believed that for any positive lambda, the diameter of the aggregate grows linearly in time. And this is proven for lambda exceeding certain value by Sidoravicius, Stauffer, and Allan Sly on in their previous works. And today's focus is on the one-dimensional case where it shows a different behavior in terms of lambda. So I'll start with defining the model rigorously first, formally. So in the beginning, at the origin, there will be a single frozen particle. And then at all the other sites, we place particles according to IID Poisson lambda. So each site will have Poisson lambda many particles, where lambda is just a fixed positive constant. And all the particles will perform continuous time independent simple random walk. So they will walk around. And when a particle right next to the frozen aggregate tries to jump left, then it will freeze and absorb to the aggregate, and the aggregate will grow by 1. And the random walk continues. And in this case, when this particle tries to jump left, and there are other particles at the same location, all the particles at that site will freeze together. And again, the aggregate will just grow by 1. And even if the particle is right next to the aggregate, it can still be active if it jumps to the right. So the question will be, if xt is the length of the aggregate at time t, then how does xt scale in terms of t, and does the scaling differ in terms of the density lambda? So let me know if there is any question on the model so far.
I have a question, Danny.
Yep.
I didn't really understand what the difference is between this and the single particle version. I mean, isn't it just sort of a time scaled?
For example,
in higher dimension, in particular, you started these multiple particles. How is that different from just starting one at a time?
Yeah, so the thing is that when you put particles one by one, or one at a time, then you need to wait until that particle attaches to the aggregate and then start the next particle. Here, like everyone walks together and then, like it's not necessarily that. So yeah, if we see the like the picture in the beginning, it's more like for the regular DLA model, it has like a kind of main branches and smaller branches with it. But then the multi-particle model, it kind of more grows like together uniformly in some sense.
So this random time scaling is changing it quite a lot.
Yeah, exactly. Yeah.
Okay.
Yeah.
Thanks.
You're welcome. And we can now
But
talk
Danny,
about.
even in dimension one, when it's not about how it looks like, you can ask different questions about what rate does it grow, and that you cannot do in the version when you have one particle coming at a time.
Yeah. I mean, the original DLA in one dimension will be very boring.
Right.
And then now in one dimension, like the MDLA aggregate is also a boring kind of line segment, but now we can talk about how fast it grows. And because it's kind of a simpler in one dimension, we can get some precise results.
Well, there is some interesting thing going in for the regular DLA if you look at the long range random walk, and even for that there are some open questions.
Oh yeah.
Even in one dimension, but
Yeah.
that's really a different model from the one you're talking about.
Yeah. Right. And that, yeah. Okay, great. So, yeah, previously, Kesten and Sidoravicius showed that when lambda is below 1, then xt should scale like square root of t, which is already different from the linear behavior in higher dimension. And intuitively, just to give an intuition, if the aggregate size was L at time t, this means that until time t, the frozen component must have absorbed at least L number of particles. But since the density is less than 1, the location of the Lth particle is like linear distance away in terms of L, and a random walk can travel by like square root of t until time t. L should scale like t to the 1/2. This is just the intuition behind why it should be square root t. And then they further conjectured that when lambda is above 1, then it should grow linearly. And if lambda is exactly 1, then it should scale like t to the 2/3. And then Allan a while ago showed the former case. When lambda is above 1, then xt over t should converge to some constant almost surely as t tends to infinity. And his method was by analyzing what we call infinitesimal speed of the aggregate. And this will also be very important throughout the talk, so we will talk in more detail later. And Dembo and Zai studied the critical case with a slightly different model, which is kind of a simplified version of MDLA in some sense. So the only difference in their model happens in so like everything else is the same as MDLA, but the difference happens in this case when there's multiple particles at the same site and one of them jumps to the aggregate. So in their model, by frictionless, each site can only be occupied by a single frozen component, a single frozen particle. So this particle will freeze and then it pushes away the other one. And then this one also wants to freeze in the next site. So it freezes in the next site and pushes away other particles if there were any. And then the particles pushed away will freeze in the consecutive site. And this will continue until they all freeze and no more freezing is necessary. So this happens instantly. And in such a case, this aggregate grows by 3 at once. So the advantage of this model is that the length of the aggregate is exactly the same as the number of particles you've absorbed. So this kind of gives you certain monotonicity condition, and by utilizing that, they were able to obtain t to the 2/3 scaling. So
I have a question. Is the
Yep.
t to the 2/3 scaling also expected when, say, in the MDLA, if you start with exactly one particle at every site?
yeah, actually, I'm gonna be discussing at the end as an open problem, but we are not sure if it's t to the 2/3. Actually, that's a good question. But if it's random with some variance, then we expect it to be t to the 2/3. But if it's like one with variance 0, then might be t to the 2/3, but not sure. Yeah.
Thanks.
Yeah, you're welcome. Oh, yeah. So here are some simulations of the model. So this is a subcritical case. So it seems like it grows like some constant times square root of t plus some smaller order fluctuation. Similar, I mean, in the supercritical case, it has some constant times t plus smaller order fluctuation. What's interesting in the critical case is that the constant in front of the leading order appears to be random. And indeed, we will see the precise result later. But let me first begin with talking about what we may mean by the infinitesimal speed. So initially, the particles are spread across the domain under IID Poisson law. And now we are going to consider the Poisson measure, not only on the particles, but including their trajectories. So we denote this measure by mu, and mu will be a law on the space of all random walk trajectories on the space-time domain. And since like IID Poisson lambda is a stationary distribution under independent simple random walk, what we can say is something like at any point x comma t, the number of paths crossing that point is Poisson of lambda. In the language of mu, we can say something like the mu mass of all paths crossing x comma t is equal to lambda. So now we define this Poisson measure mu, and I'm going to introduce the aggregate here. So this thick blue line is the plot of the history of the aggregate until time t. And if we want to consider how fast this grows, the only important factor is how many particles you have right next to the frozen aggregate at time t. So yeah, I kind of hear some echo, but yeah, wonder if this. Okay. So okay, so I want to claim that the number of particles right next to the aggregate is distributed as Poisson, and this can be observed as follows. So we previously defined the Poisson measure mu, which was a measure on the space of all random walk trajectories. Now we want to split this space into two parts. One is the space of paths that intersect with the history of the aggregate, so this thick blue line. And the other is the space of paths that does not intersect with this. And conditioning on the history and considering the active random walk paths that crosses this point is equivalent to consider the Poisson measure on the second space. And since by the Poissonian property, if we consider like two independent Poisson processes on each space and sum them up, then it will recover the original process. And therefore, the number of active paths, crossing this point will be also distributed in Poisson. So we're going to define the infinitesimal speed as the half times conditional average number of particles right next to the aggregate, where this 1/2 comes from the fact that each particle jumps to its left with rate 1/2. And then with this S of t, we see that xt is a Poisson process that grows with rate S of t. Any questions on the formulation of the speed? Okay, so let me move on to the results. So
why the +1 in the definition of ST?
oh,
at location xt +1.
Yeah. Location xt +1 at time t. Yeah. Right. Okay. So before discussing the result at critical case, I'm gonna mention some interesting stuffs. What happens in the mildly supercritical case when lambda is slightly above 1. So Allan showed that this xt over t converges to a constant, and if the phase transition picture we have is correct, then this constant should converge to 0 as lambda tends to 1. And Sidoravicius Rath conjecture that this actually scales like lambda minus 1 over 2 as lambda goes to 1. And they came up with this result from the following heuristics. So in the initially in the interval of 0, c times t, since the density of particles is lambda, we will see lambda times ct particles in stationarity, which means that when aggregate grew up to the point c times t, it must have absorbed like lambda minus 1 times ct excessive particles, where by excessive particles, I mean just the total number of particles absorbed minus the length of the aggregate. So like the particles that are packed in the same site, like with others. Okay, and there is another way to count this, which is the following. So if n is the number of particles at space xt plus 1, so right next to the aggregate, then the jump rate to the left will be n over 2. And when one of them jumps, we are going to add n minus 1 excessive number of particles. Therefore, the excessive particles are added at rate 2 times square of the speed. So if the speed is like c, then the excessive particles are added at rate like 2 times c squared. So 2 times c squared should equal to lambda minus 1 times c. And they came up with lambda minus 1 over 2 from this identity. It actually turns out that this constant c lambda scales like lambda minus 1 over 3. So what was wrong from this heuristic is this assumption where they set s equals c. So what actually happens is that the speed does not become concentrated as t goes to infinity, but rather follows an SDE at all times, which I will discuss later in more detail. And also this excessive particle heuristic kind of gives how to get like t to the 2/3 scaling in the critical case. So if the aggregate at the critical case is of size t to the alpha at time t, then the number of particles we see in the interval 0 and t to the alpha is like t to the alpha plus some t to the alpha over 2 fluctuation. And if we believe that this fluctuation should correspond to the number of excessive particles, then excessive particles are added at speed squared multiplied by t. And if we solve this identity, we get alpha should equal to 2/3. Okay. So this was the result on mildly supercritical case. Now we move on to the critical case. So we were able to show that it scales like, not only scales like t to the 2/3, but also got its scaling limit. So it's described by an integral of a diffusion, which solves this SDE given by dRt equals 2 times r to the 5 over 2 times dBt. And here, this initial condition of r0 equals infinite should be understood as like the limiting process as you set r0 equals to m with the same law, same SDE, and then you send m to infinity. So to say a couple things about r, it turns out to be a self-similar process. So if you rescale it by minus t to the minus 1/3, you get the same law. Also, it's kind of not difficult to see that every self-similar process should be a power of a Bessel process. And Bessel process is like 1/2 self-similar. So it turns out that RT is minus 2/3 power of a Bessel process with dimension 8 over 3. And this 8/3 is more of a result of a computation, but we unfortunately don't have a better explanation on the intuition, like physical intuition behind why it should be 8/3. And also the aggregate size of aggregate is given by integral of r, and r corresponds to the scaling limit of this infinitesimal speed, which we discussed just before. But after some appropriate smoothing, and we will later see that S itself is actually some chaotic process that's very difficult to study. And in the mildly supercritical case, a similar result holds. So in this case, we obtain a different diffusion where we have the same diffusive term, but now it has a drift term. This is no longer self-similar, and indeed, it converges to some stationary process at the end. And it's the stationary measure, we can compute its mean by applying like standard Ito calculus techniques. And we get that its mean is equal to 1/3, which corresponds to the lambda minus 1/3 result in the previous slide. So any questions on the results? Or
Why are
anything
there
else?
quotes on the convergence?
Oh, so again, like the S itself wouldn't converge to this diffusion, but we need some appropriate smoothing procedure. This holds for like,
Right. Okay.
yeah.
Thanks.
Yeah, I'll talk more about this later. So from now on, we are going to go deeper in how to understand this infinitesimal speed is, and then I'm gonna explain some of the main steps on how we get to the scaling limit of S or its smoothed version. So we saw that if we define S to be half times the conditional average number of particles right next to the aggregate, then xt is a Poisson process with rate S. So here again is the picture. In terms of so recall the Poisson measure on the random walk trajectories mu, then in terms of the language of mu, we can say that S is equal to half times the mu mass of all paths passing this point, which also avoids the trajectory of the aggregate. And since we are interested in the paths that ends at this point, we can rather think about the paths starting at this point and moves time backwards and avoids the random walk trajectory. So to express this in a more convenient way, I'm going to switch the axes in the sense that this light blue part of the aggregate comes to the origin. So we swap the axes and read the process backwards in time, where I define yt of s to be xt minus xt minus s, which I call backwards aggregate function, and it encodes how much you have grown in the recent past of time s. And now we are interested in the random walks starting from this point, and that avoids this given trajectory of backwards aggregate function. Okay. So this in this picture, the random walk starts from -1, but it's always better to make it start from 0. So I'm going to push this one step above. Now I'm kind of allowing them to overlap, but W should stay, shouldn't exceed the level of Y. So we can write ST in the following form of, so ST is equal to lambda over 2 times the probability where W stays at most Y at all times, given Y. So here I multiply it by lambda because in the previous expression, this mu measure already carries the lambda mass in this expression. But now I'm considering only a single trajectory of a random walk, so I need to multiply the initial density lambda over here. And then again, xt will be a Poisson process in S of t. And also this backwards aggregate function yt can be interpreted as a function valued Markov process where it grows by 1 with rate s of t. So any questions on the definition of ST? Maybe this is the good timing to ask because the further discussion will stem out from this expression. So far we have derived some formula for S, but we essentially didn't do anything because our goal is to understand xt or yt, but then in the expression, it still contains this conditioning on yt. So
what's the relation between st and yt? Is one of them a function of the other eventually? I mean, does one of them contain all the...
yeah, so y is essentially the same as x. So we have, if we have x, then we can, basically define y in this way. And using y, s can be defined by this conditional probability. Yeah, so s is a function of y.
Yeah, okay, so all the information you need from the model is in y of t?
Yeah, so y of t contains the information on the history of the aggregate until time t, and then st will give you how fast it will grow in the infinitesimal, time interval like t and like t plus delta.
Mm-hmm.
Does that make sense? Okay.
Yeah, okay.
So, okay, so as I said, we still have no understanding on what y is. So the natural thing, what we can do is kind of plugging in another function we can understand better in the place of y. So this speed process can be defined in terms of any increasing function. And a natural candidate is to substitute like a fixed rate Poisson process, pi, which basically means that we are assuming that the aggregate is growing at a fixed speed until time t. And the obvious advantage here is that now this y minus w will be pi minus w, and it's just a continuous time biased random walk. So for instance, we can conveniently compute the expected value of s of pi using the fact that this is a martingale. So if we set the capital T to be the first time where w becomes larger than pi, then it's just estimating the probability that t is equal to infinity. We get something like lambda alpha minus 2 lambda alpha squared plus some lower order terms. So just to get some intuition, let's assume that s of pi is very close to its expectation. And then what it means is that if xt has been growing at like fixed speed alpha until time t, then from now on, it will grow at some speed given by lambda alpha minus 2 lambda alpha squared. So if our lambda was greater than 1, so if we were at a supercritical case, then this tells us something in the following sense. So let's assume that the speed of, so aggregate has been growing very slowly. So alpha dropped to a very low level. Then by this advantage in the leading order term, the speed starting from time t will be larger than the speed you have been growing until in the past. This means that the speed cannot be very low because if it's very low, then it has a tendency to push up in the future, which gives us some kind of a mean reverting property. And this was the main ingredient to show the linear growth in the supercritical case and the previous work of Allan. And to make this rigorous, we need to come up with some good approximation of the backwards aggregate function so that you don't harm the advantage you get from the leading order.
I'm sorry, I think I missed something. In the first displayed equation, there's a little t. Is that in the infimum? Is that supposed to be infinity, or does this depend on t?
Yeah. So this should be infinity. Sorry. So if this were yt, then yt is defined to be infinite when s is larger than t, so it doesn't matter. But if it's general y, then it should be infinity. Yeah, you're right. Thanks for pointing out. Okay, so the main problem in the critical case is that if lambda is equal to 1, then you cannot gain any information from the expected value of s, which is kind of what we can naturally expect. So now what we need to do is to precisely understand the fluctuation of the actual speed from its expectation. So the further part of the talk will be focused on like kind of high level understanding what the fluctuation is. So let us define the compensated Poisson process by pi star, where we subtract its mean from the original Poisson process, and it becomes a martingale. And then s of pi, now assuming lambda is equal to 1, is equal to half times the probability that the stopping time t is infinity. This t was the first time where w is larger than pi. So one convenient way to study the fluctuation is to study the infinitesimal difference as we reveal more information. So we can use the dupe decomposition and obtain this kind of formula where its fluctuation is written as an integral of h in terms of the compensated Poisson measure. And particularly in this case, it's more convenient to work with the event capital T being finite rather than t being infinity. And if t is finite, the non-trivial contribution from this infinitesimal difference comes from the event where t is finite but still larger than s. And that's why we have such a definition for h. And now if we consider the expected value of hs, it reduces to some hitting probability estimate of a biased random walk. So for instance, it must scale like 1 over square root of s times e to the minus this exponential decay, where this 1 over square root of s decay corresponds to the local central limit theorem type estimate when s is small. When s gets larger, then basically you cannot overcome the biased part anymore by the diffusion, so it will decay exponentially. One thing I want to stress here is that eventually we want our speed to scale like t to the minus 1/3. And if our alpha is the level of t to the minus 1/3, then by this exponential decay, we don't need to see the past further than the order like t to the 2/3. So things happening like before then alpha to the minus 2 scale would have negligible effect. This means that when we consider the speed at time t, we only need to reveal like the relatively short period of history. Okay, so that was one thing. And also we can precisely compute the integral of expectation of hs, which is basically the first moment of our stopping time t, and we get this constant. Now we're going to define this ks by normalizing this expected value so that integral of k always equal to 1. Okay. And this will be important in the next slide. So far we had this elementary expansion using dupe decomposition on the speed. And we saw this expectation of speed is equal to alpha over 1 plus 2 alpha. We defined this k to be a quantity that has that integrates to 1. So now what we do is split this hs term into expectation of hs and h minus expectation of hs. So the second part becomes this term. And with some little bit of rearranging the terms, we get this expansion for s. And one thing I just want to say here is that this red term of the integral of k gives the leading order of order alpha. And the other two terms contribute by a smaller order. of alpha squared. But eventually, we will have to understand the smaller order terms as well. But for this talk, we are going to focus on how to interpret this leading order. So, okay, so to understand what this leading order is, let's say that our speed was actually given by just this red term. So s hat is equal to the integral of k dy. And then we generate x hat as the Poisson process of s hat. Okay. So what can we get from this kind of simplified process? Well, first of all, s hat is equal to the sum of k's because dy is 1 when y has a jump, and otherwise it's 0. So it's actually summing up k of t minus ti, where ti is the points where the aggregate hat jumps. And furthermore, we are going to interpret this sum in the following sense. So this basically is the rate that xt grows. So xt grows by like rate s hat. So it will become, it will have additional jump between time t and t plus delta with probability s hat times delta. Each jump at time ti, let's say it contributes by rate k t minus ti. So it gives rate k sub t minus ti times delta, like probability of adding extra jump. And let's say this extra jump from ti, let's interpret this as a child of the jump at time ti. Then the average number of total jumps in the future given by ti is obtained by the integral of k, which is equal to 1. So we can see that this x hat can be interpreted as a critical branching process. So each jump at time ti will land additional jump at time t with rate k t minus ti. So the edge lengths will have density k. And then we can also compute this average length of edge, which turns out to be roughly like 1/2 times alpha squared. And then everything is Poisson. So the mean number of offspring is 1 for each jump. And actually, its law will be Poisson of 1. Okay, so any questions on this critical branching process interpretation of the speed? Yeah, so just to repeat once more, I think what I want to say is that each jump contributes by this much amount of rate. And if we integrate that out, then it's equal to 1, so that each jump will land an average 1 more jump in the future. So it's a critical branching process. And then the location that the additional jump lands is kind of random, which is determined by this density k. Okay. So now we want to obtain the scaling limit of s hat. So if it were a discrete time Galton-Watson critical branching process, then the number of offsprings at each generation forms a martingale, and we can obtain its limiting diffusion like kind of straightforwardly. But then since its edge lengths are continuous, s hat is no longer a martingale. So even if you have the same value of s hat, you need to know the precise profile of the particles at the past to obtain to describe the future branching of this process. So indeed, we kind of expect to see the scaling limit of s hat to be some white noise convolved with a kernel given by k, which is not a Markov process in particular. So basically, s hat might not be a good object to study to derive a scaling limit because it might not converge to a Markov process at the end. So basically, we want to consider a substitute of this, which is the smoothing process I mentioned in the beginning. And we kind of want to consider the corresponding analog of this continuous edge length branching process. So what we consider here is the density at infinity. And to get this, we first consider this K star, which is given by the sum of all convolutions. And K star basically gives the density at time S generated by a single jump at time 0. So it can be either like a direct jump or like a children of a children, and kind of combining all those possibilities. And as S tends to infinity, it will converge to like 2 times alpha squared, which is the inverse of the average branching length. So by the density at infinity, I mean that this L hat defined by the conditional expectation of S hat given the information up to time t, and letting this u tend to infinity. Also, it can be described as the following formula, where it means that each particle at time t, ti, lands a jump at time u at rate ku, and that will contribute by k star infinity at as a rate at infinity. Okay, and a better thing about this L hat is not only it's a martingale, but also we have a nice formula for its infinitesimal difference. So DLT equals to 2 alpha squared over 1 plus 2 alpha times this term, where in this case, this integral of ks in terms of dy hat equals to s hat, and x hat is a Poisson process with rate s hat, so we kind of see that it's martingale, which should be the case. And another reason why we didn't want to directly look at S hat is that it shows a chaotic behavior, which is described by this simulation. So one way to think of this is the following. So S hat was given by the sum of k's, and whenever an extra jump is introduced, then S hat will increase by k of 0, roughly. And if we actually compute it, then k of 0 turns out to equal alpha. So that means S hat changes like by its own scale. So like alpha becomes 2 alpha after a jump is introduced. And that's why it shows like this chaotic spikes instantly whenever a jump is introduced. And then it very sharply decreases to its original level by the decay property of k, while L hat kind of smooths out that kind of spikes and then gives like a more moderate kind of diffusive process. So S hat will basically show a too large like variance to obtain like the scaling limit in the ordinary sense, where we specify this infinitesimal increment of like mean and variance, and then obtain like the Ito type diffusive scaling limit. And S hat wouldn't be appropriate to do such a thing. So for L hat, yeah, so now our goal is to characterize the infinitesimal increment, the first and second moment of the infinitesimal increment of L hat. And we expect to have like 0 incremental mean because it's martingale, of course, and like 4 times L to the 5th times delta of variance, because in the discrete time Galton-Watson branching process, the number of offsprings at each generation has a scaling limit given by dzt equals square root of zt times dbt. And here we have continuous edge lengths, which is roughly like 1 over 2 alpha squared at average. So it kind of slows down our process by 2 alpha squared. And therefore, we expect this variance to be like 4 times L to the 5th times delta. Okay, so although obtaining these kind of estimates is not like trivial, but let's say we can do this because it has like a critical branching process structure. Our main goal is then to translate this result into our original aggregate, which is LT. So our plan is kind of to couple the original aggregate with this critical branching process interpretation under this like relatively small time interval t to t plus delta, and show that they kind of has the like kind of coupled together nicely, and we can control like the difference between the two. And there are several main obstacles in doing such a thing. So first thing, I kind of didn't explain the details so far is why, approximating the aggregate process by the fixed rate Poisson process is valid. And the way we see it is by a multi-scale analysis, showing that if they kind of stay close together in appropriate sense during the time interval t and t plus delta, and then in the next time interval, starting from t plus delta up to say t plus delta prime, it's likely to stay close together with high probability, given that they were close together in the previous step. And also another issue is to adjust the scale of alpha. So alpha is basically the scale of the speed during the interval t and t plus delta. And then we need to appropriately change its scale in the next step. And we need kind of a procedure to do that properly. And also in the expansion of the speed, the critical branching part was the main order, but then we had like the other smaller order term, which also need to be understood precisely. So I won't go into like any of these points in detail, but I'm gonna jump to the end and see how we can obtain the scaling limit at the end using kind of these elements. So we had this expansion on the speed, and the goal was to compute the conditional mean and variance of the increment. And we also had this formula for DLT. So we are going to split this part into martingale part and the drift part, where martingale part will contribute to the incremental variance, and the drift part will contribute to the incremental mean. So for the variance, it's kind of slightly simpler. So if we believe that S kind of stays close to alpha during this interval, t and t plus delta, it will give us like 4 alpha fifth times delta, which is the scale what we want. And for the drift part, this integral of k dy is equal to the main order term. And actually, this constant here is slightly smaller than 1. It's roughly like 1 minus 4 alpha. So in the integral, we have like 2 alpha squared, which comes from this term, and minus 4 alpha squared, which is minus 4 alpha times alpha, which is given by this. And then I've never talked about in this talk, but it turns out that this term scales like 2 alpha squared plus some smaller order term in its expected value. So kind of the leading orders cancel out, and we get like little of alpha to the 4th times delta. And this kind of two correct estimates on the incremental mean and variance leads to the scaling limit at the end. So just to say one thing about the drift part, in the early phase of our research, we didn't expect at all to see such a cancellation. And so we kind of expected to have some non-trivial drift term, but it turned out that they had cancellation, and I thought it's kind of cool to have this and end up with a simple scaling limit. But Allan, on the other hand, was a little bit disappointed of this cancellation. I think he wanted kind of a more intimidating limiting diffusion, including a drift term. But yeah, that was a story. And then, okay, so to summarize today's talk, we see we saw that xt is a Poisson process where it's infinitesimal speed given by this formula, which had the mean reverting effect in the supercritical case, which led to the linear growth. And we were able to expand using the dupe decomposition to study its fluctuation from its mean. And this red part gave the leading order, which can be interpreted as a critical branching process with continuous edge lengths. Also, this speed itself turns out to be not a good object to study when we want a scaling limit, so that we instead consider the density at infinity and derived its scaling limit instead. Because S is not a martingale, and also it shows a chaotic behavior. Okay, so I'm going to conclude the talk mentioning an open problem that we think it's interesting. So we can ask what happens when the initial distribution is not Poisson, but given by some arbitrary probability distribution. We think if its variance is positive, then we still expect to see t to the 2/3 growth, but then the limiting diffusion is different. So the speed will be, again, like some minus 2/3 power of a Bessel process given by this dimension. And one interesting thing here is that the Bessel process is recurrent when its dimension is less than 2, which means that our speed process will hit infinity like infinitely often, which gives, if variance is like larger than 2, then our scaling limit will not be differentiable. We thought it's kind of an interesting thing that happens in this model. And also, if sigma is 0, we don't have a clear idea what this exponent should be. It's kind of also an interesting question to think about. Okay. So I'll stop here and thank you for your attention.
Thank you. I think we can unmute everyone. If I can. Well, we can all unmute individually to thank Danny. So.
Thank you.
Thank you.
Thanks.
I will stop the recording.